without any, POGIL or lab, you would totally understand all this, and you would just really understand the principles behind plugging the numbers in the formula. No, I'm not doing that. All right, so anyway, let's get into some things that we had talked about yesterday a little bit more. The thing about gases is they're going to expand to fill the volume of the container they occupy. I do want to hit on this with solids, liquids, and gases and how they behave inside of a container. And so if I have a container and it has a lid on it, right, there's my lid, and I have a solid piece of ice, like it's not going to take the shape of the container, it's going to keep its own form, and so that's what a solid does. If I have liquid water in the container with a lid, it's going to take the shape of the container, but it's not going to completely fill the container. And so this is a liquid, it takes the shape, but it does not completely fill. Doesn't fill. So it doesn't fill the container, but it does take the shape. So a liquid takes the shape of the container. And then if I have a gas stove with a lid, the gas will take the shape of the container and it will completely fill the container. So that's the difference there. It makes a homogeneous mixture. Right now you're breathing in and out the atmosphere, which is a homogeneous mixture of mostly nitrogen, 78% nitrogen, 21% oxygen, 0.9% argon, and then other trace gases. It has a low density, and remember, density is mass divided by volume, so you have a really kind of low amount of mass in a volume. It's compressible. We can compress the gases all the way down to being a liquid if we put enough pressure on them. But you guys know, I mean, you heard like air compressors. Your air conditioning, your refrigerator works by compressing air and then letting it cool. Let me show you. Take your hand and just open your mouth wide and blow on your hand. Close. It's hot, yeah? Now make your mouth a small circle and now blow. Yeah, so when you, I know it's a different temperature. I've done this before. Is it cooler the second time? Yeah. So what happens is when you compress a gas and then, you didn't like my little dance there? What are you, a judge on America's Got Talent? I mean, that was a good dance. I've turned red. I lost my train of thought, hopping back on the train. When you blow and you make a small aperture with your mouth, we make a small opening, the gas expands as it comes out of your mouth. And so as gases expand, they cool. That's how your air conditioner works. That's how your refrigerator works. It has an air compressor, and then it lets the gas expand, and that's how things cool. Unless you wanted to explain that to me, or do a dance, which I think I got you on both. So anyway, and they exerted pressure. We had talked yesterday about what pressure actually means, and so let's kind of continue that. What pressure is, I mean, you don't really need to know this formula here, but pressure is just an amount of force over an area. And so when, if I press on the board, remember the first 5 letters in pressure or press, like I'm exerting a force on the board over an area. And so the gases in this room, they are bumping up against you and exerting a force. They are bumping against the walls and exerting a force. And so that's pressure. And so each collision with a gas exerts a force. And if I keep the temperature and the size of a room or container constant, the pressure is going to stay constant. So here's somebody spent a long time drawing this little man here. This is detailed. But, inside your nose, inside your ears, on your face, on your head, on your legs, all around you and above you and below you, there's 1 atmosphere of pressure. Okay, and so because you have 1 Earth's atmosphere above you and around you, and so if we have like a high pressure come through, we might see pressure above 1 atmosphere. If we have a storm, it might be below 1 atmosphere. There are other units for pressure. For this class, for you, we are doing this kind. So in a minute, we're not going to convert. All right, so what I want to do is I'm going to crush the can, and I'm going to then tell you how this works. All right, so if you want to come up here, you can see the things. Yay! Okay. Okay, so when you do this tomorrow, pay attention because it won't work, okay? I want to have a slow-mo contest, slow-mo video contest on this. But when you do this tomorrow, you're going to use your beaker tongs, right? And when you pick it up, you want to submerge it straight down like this. Oh.
Yo.
So, I know, right?
It just.
So you can't be like, take it half, blah, blah. You need to do it that way with the open side down, or it won't work. That would be so cool. I was trying to. I gotta heat up another can. If it can, it takes a minute.
No, this is my Batman can.
No, I can't do it yet. I gotta come back and just do me. Like, we gotta keep, this has to be boiling. Alright. Y'all look all sad about it.
That's the Batman can.
Y'all will get to do that tomorrow because you brought in so many cans. That's why I want everybody to do that because that's fun, right? If you don't do it right, your camera question, then I'll pay for you. It's so
That's okay. Yeah.
What? Where's my pen?
I don't know, but that's
Is it recording?
What? Yes. Hey, have y'all seen what happened? Is everything okay?
That's my can.
Hey, have y'all seen my pen that I used to write on the board? I found it. Hi. So let me explain what happens here. Alright, so what we see on this left-hand side, and this has to do with the vacuum. It doesn't matter. We don't need a vacuum. So what's happening here, and I'm going to make my little dots of water. I'm actually going to make them blue because that makes me happy. And so these are like little water. This is water vapor, water as a gas. And so don't worry about that part, don't matter. So as I'm heating up that water right now, what's happening is I have some liquid water in the bottom of the can, but it has to be boiling for it to work. If I went over there right now, it would not work. 0 things would happen, okay? So the reason it has to be boiling is because I have to have water molecules in a gas form going and moving around the inside of the can. And so let's see, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 gas molecules. And of course that's not really 12, it's probably like 12 bajillion. That's fine. So anyway, what ends up happening when I take and I invert the can over the ice water and into the ice water, I'm going to rapidly cool those gas molecules, and somebody said it, I'm going to make them condense. And so when they condense, that literally means to go from gas to liquid form. And so here's my water in the bottom of the container, the water that was boiling. And so a lot of those gas molecules are actually going to, like I might have 4 left, the other 8 are actually going to become liquid water. Does liquid water exert a force on the inside of the can like gaseous water does? So basically what I've done here is I've reduced the number of moles I've reduced that number of moles of gas inside this container, and since that can is flexible, your cans are flexible. They really are. I mean, you can squeeze a can, right? Since that since that Coke can is flexible, the inside pressure and the outside pressure have to be equal, and so that volume is going to shrink to accommodate that. So the reason it has to be done in ice water is not because like the ice water has more pressure than, tap water. It's because I need it to be cold enough to take some of those gas molecules and turn them back into a liquid. Then the inside of the can's not going to have as much pressure. And we talked about pressure and volume yesterday. When pressure goes down, the volume's going to go down. Or excuse me, the pressure goes. Yeah, I know. They're direct. They're multiplied. They're indirectly related. Okay.
As the pressure.
Well, really, we're talking about moles of gas here. So I think I just refer to like 5 of the variables. Let's just stick with moles and volume. How about that? But the pressure and the volume, that really has to do more when you're thinking about those flexible balloons and stuff, when they can expand and contract. And so we're talking really about the moles. So let's just stick to those 2. And we're going to do some math with the pressure and the volume together. That's Boole's law. So how do you feel about the moles of gas and the volume here? You feeling okay about that? You kind of get why the can crushed. Pretty interesting, right? So anyway, moving on from there. Yeah, the thing about the ideal gas law is you have all those different variables and you can kind of separate them out. And so when you start thinking about too many of them, it does get a little confusing. So barometers, if you've ever heard or you watch the, if you ever watched the weather, I love weather, but if you watch, they'll talk about millimeters of mercury for the barometric pressure. And so millimeters of mercury literally means 760 millimeters of mercury means that the air pressure is high enough to push the mercury in a tube 760 millimeters, which, you know, pretty cool. So just for fun. There are some things about gases that you need to understand. The biggest thing is, though, like the temperature of a gas is really just related to how much energy it has. And so the average kinetic energy of something is its temperature. Temperature, people have trouble with the definition of temperature, and that's a sticking point. We'll get to that next year for a lot of you guys. But basically, the higher the temperature, the more energy it's going to have to move around, rotate, vibrate, and that's a whole nother lesson. Not that you won't get to. So there's this theory about gases. It's called the Kinetic Molecular Theory, KMT. So what KMT says, it has a couple, I think it has like 5 or 6 postulates depending on what source you're looking at. But what happens with gases, according to KMT, is that when gas particles collide with each other, energy isn't really lost. They're just elastic collisions, which means that no energy is lost, energy is conserved. And so this theory is really idealized, and it's not completely accurate as far as like what really happens with gases, and that's a whole nother thing next year. But anyway, I'm gonna just pause this for a second so I can tell you about Boyle's law. So that's Boyle's law: pressure and volume equals pressure volume. We talked about this yesterday. When they're getting multiplied by this, you have to think about that mathematically. And so, you know, when I'm doing questions like this and I'm having to think about the relationship, if it's hard for you to think about that, put some numbers in. Like if 4 has to equal 4, and you start out with 2 and 2, if volume goes up to 4, then pressure has to go down to equal 4. So like put numbers in and think about it. If you can't do it in your head, then do it with math. So there you go. So they're inversely related because one has to go up as the other one goes down. Pretty simple. And so pressure and volume, you can see that as the volume is decreased, then I'm going to have twice the pressure. And that goes both ways. So Charles's law. Have y'all heard of Charles Barkley? Charles Barkley, he played basketball.
Yeah.
Who has not heard of Charles Barkley? You guys, have you really not heard of Charles Barkley? How are you, like,
Yes.
alive?
Play baseball.
Oh, the internets don't work. No, I'm gonna look it up. It's worth it. It's worth it to tell you. I don't care. I don't know what that means.
And then puts the things to the right. That's bottom.
Oh, I can be unsafe. What if
You can be unsafe.
you know where that's going? You have to admit that's funny. Do you get it? No? Okay. So here's Charles Barkley. Laughs to himself. He doesn't look familiar?
You played with his son.
No, he looks like he's in the movie.
Oh, was he the one in that? No, that was Michael Jordan. I don't know. He was in Space Jam?
No, my Jordan was in Space Jam.
I just said that. I just said no, that was Michael Jordan. So anyway, that's Charles Barkley, and he plays basketball. Can you remember that? I bet he still plays basketball in his driveway.
No,
Where he
golf.
fine. Alright, so here's Charles's law. Charles is very tall. If you don't like it, then don't remember it. And so here we kind of think about these guys getting divided. When they're divided, they're direct relationship, and that rhymes and everything. Or not, doesn't rhyme, has alliteration. But whatever, I give up. So if I'm looking at these numbers, I see 2 numbers have to be equal, or 2 sets of values have to be equal, so 2 equals 2. So basically, if I start with, 4 and 2, that equals 2. And like, if we double volume, then the temperature also has to double, so it still equals 2. You see what I mean? So that means they're proportional because Now, here's the thing. All these gas law questions have to be done from Kelvin because Kelvin is based on kinetic energy of molecules with zero being like no molecular movement. That's you have to go. You have to go to Kelvin. Just trust me. So anyway, the good thing about the conversion to Kelvin from Celsius, you can't use Celsius at all. On this yellow sheet here, the conversion from Celsius to Kelvin is about the. I don't know. It's on here. It's about the fifth. 1, 2, 3. I'm upset. Fifth thing down over here with gases. So to go from Celsius to Kelvin, you just add 273. Do you guys see that? All right, so whatever. So any of these calculations with temperature, you do have to go to Kelvin. And you're just going to do that by adding 273. I'm having a psychic vision of somebody asking me, this room had to go to Kelvin. And I'm going to say, it's on your yellow sheet. Sit this one down. Do you hear me saying it? Because I can hear myself saying it. I should open up a hotline because that's going to happen. Relating volume and temperature. This is going to help you. I'll have you a little bonus question here in a minute. Anytime you have something that's directly related, y'all know, like if I wanted to write 1/2, like that's how you write a fraction. Anything that's in a direct relationship and is divided, the line looks like a division bar. When you have okay, so like volume and temperature, it's volume over temperature. The line of the graph looks like a division bar. Like you don't write, I can't even do it. Like you can't. Do you see what I'm saying now? Like the slope of the line is the same as a fraction bar. What?
You're like 3 or 4, that's right.
There's nothing wrong with that.
I think that's great.
You mean like straight across, like horizontal?
Or if you were like,
I don't care. If you don't like that, then don't use it, but that's the thing. Okay? Pretty sure that's a normal way to write fractions. I'm feeling good about it. Anyway, temperature and volume. If we reduce the temperature, we're going to reduce the volume of the gas because this is how hot air balloons go, right? If you're floating in a hot air balloon, and they got that flame just a burning, you know, your balloon's going to be pretty big, and then you're going to be buoyant enough to float around, have like a romantic like picnic. People do that. I'll throw up. That's a bad idea. But I'm scared of heights. Anyway, if you cool down the balloon, then it's going to get smaller, and then you get to come down hopefully peacefully and slowly instead of die. Temperature and volume. When you see if we decrease the temperature, the volume also decreases. So those are directly related. So if they're directly related, they're like a little division problem, right? You see? Oh, are you okay? Okay. Combined gas law. So I have a story. Of course, I have a story. Y'all like my stories? So anyway, have you guys heard of, or do I need to Google this too? Have you heard of the Silver Comet Trail?
yes.
Yay! Okay, if you haven't, I'm gonna draw a picture. So.
You haven't heard of Silver Comet? I've been on it.
Okay, so the Silver Comet Trail was actually just like a railroad track, and nobody used that rail line anymore. And so, like it was like a little railroad, and then trains went up and down it. And so, then what happened was, there we go. So those are railroad tracks, okay. And so then, what happened was they paved it, and now people ride their bicycles on it. I'm drawing things. Y'all know I'm good at drawing, right?
Nice.
That looks good. That's good for me. That's good for me. Okay, wait. This is floating.
What's going on?
There you go.
Those are the handles.
That looks good.
He was holding on to the floating hand. He only has one arm.
That's good for me. Are you guys okay back there?
No.
I hope you're wearing a helmet. Hang on.
Safety first.
Safety first.
Why do they only have one arm?
It's like when you're looking at her from a side view.
Look, see, I have one arm. See? Okay, let's come back together. Okay, so what they did was they railroad track and they paved it. So they paved the track, okay? So they paved the track. So and then this is the division bar, see?
How did you come up with that?
I made it up. I just made it up. So they paved the track, okay? And so it's PV over T. This is the combined gas law. Can you remember that? Or are you going to remember that? They just have one arm. Okay, so PV T equals P2 V2. So basically one set of pressure, volume, and temperature equals the second set. And so I'm going to work one of these out for you, of course. Now again, anytime you have temperature, you're going to have to add 273 to anything that's in Celsius. If it's already in Kelvin, then leave it alone. But a lot of times, just to be a jerk, they'll give you things in Celsius. So anyway, how do you feel about that? Do you feel comfortable putting numbers in here and then solving for the one you don't know? Yeah, me too. Good. So let's go ahead and look at a couple of these. Okay, so when I'm solving for a variable, you need to do this too. I'm like telling you, you have to. I'm saying it out loud. What you need to do is you need to write the formula first. And the thing about the combined gas law, whatever you don't need, you can just cover up and not use. Let me show you what I mean. So the combined gas law problems are all going to be the pave the track. So they're paving the track. Okay? So I'm kind of sad that one's going off the side of the page. Go ahead and write down your formula though, and I'll just scooch this over and be happy. So pave the track equals track. And so this is my first set of conditions and my second set of conditions. So let's read this. The cylinder of gas is kept at constant volume. So, slap your back. Which one of these am I not going to need to use at all? If it's kept at a constant volume, is it going to change? No. So what I'm going to do is I'm immediately just going to X that out. So I'm left with P1 over T1 equals P2 over T2. Do you see how I did that? Was that a magic trick? So what's going to happen on these? Sometimes we'll need to use all three, but if it says, hey, this stays the same, then you don't need to use that one. You can just mark it out because it's not going to change anything. As the temperature increases from 24.1 degrees Celsius to 326.4 degrees Celsius. So as I'm reading the question, I'm piecing this together as I read. As soon as I see anything about temperature in Celsius, what I need to do? You just go ahead and so just get your little calculator out before you start the problem. Get your stuff straight before you start. So 24.1 plus 273. Why am I using calculator? 290. So it goes from 297.1 degrees Kelvin to 326.4 plus 273. 599.4 degrees Kelvin. Have I blown your mind yet? Are you okay? Everybody fine? Alright, so if the initial pressure was 110 atm, and we're just going to solve for the final one in atms, that is okay. You want to go to millimeters of mercury, there's a simple conversion, not a big deal. You want to do that? Fine. I'm not doing it. So what I'm going to do is I'm going to rewrite the formula that I need, P1 over T1 equals P2 over T2, and then I'm just going to fill in the stuff that I know. And so my first pressure is 1.10 atms. Because it says the initial. That means the first one, the one with the 1 on it. How you feeling? My first temperature was 297.1 degrees Kelvin. Have I lost any children yet? Everybody happy? Alright, the second pressure is, I don't know, because they do the things where you circle. There you go. I know I'm solving for the second pressure. So the second pressure, I'm just going to rewrite that variable because that's what I'm solving for. And the second temperature is 599.4. Now, people get freaked out when they see numbers and stuff. I don't understand that because I know you went to the 4th grade. So go with me for a second. Back to the bicycles. Just kidding. In math class, when you were like 11, okay, if I ask you to solve for x, what would you do? Have you seen that before? Would you not just be like 35 is equal, like you do the things, 35 is equal to 4x. Have you seen that before? And then you solve for x, can you divide? Can you do that? Can you do that? Can you do that? Alright, so let's go back to the board with crazy numbers. Guess what you're about to do? you're going to divide by 297. So y'all go ahead and do that with your little numbers and your calculator. And honestly, I'm perfectly okay with you guys just writing down the formula, writing down the setup, and then doing it in your calculator. I think that's easier. So when you start to write, that's not necessary for you to write any more than that. Watch your sig figs. Well, here's the thing. These Celsius temperatures, the sig figs for these are the sig figs that they are when you convert it to Kelvin. So this is really, you know, still going to be 4 sig figs, even though it's only 3 right here. See what I'm saying? These Celsius don't count. The sig figs for the temperatures are from the conversion to Kelvin. So, anyway, I'm still limited by this pressure, 3 sig figs, right? So I get 2.22. You can do whatever you want. As long as you show me the setup, do that, yes. So there's your answer. Does anybody have any questions about how to do that? That's pretty nice after the stuff we've been doing, I'm not gonna lie to you. I like this game. I feel like there's something else. What?
The next one, do you want to read the element, or like
They're always
back to back to
I'm not, we're not going back to Celsius. You don't go back to Celsius, that's not a thing, you're not doing it. Just trust me, just look,
Alright.
I promise. That is not necessary. Okay, so if you did want to convert it to millimeters of mercury, which is just another, that would be like saying, okay, let's say take the answer in feet and go to meters. We don't need to do that, but if you did want to, it's just a one-step conversion. I think I put, oh, you know what, in my calculator I did 1.10, but whatever, it's 2.04. I just put the wrong number in my calculator. But if you wanted to do the conversion, this conversion right here is actually on that yellow sheet. It's not a big deal though.
It was one. They did it.
Oh, this is the first time in my entire life that I have messed something up. Alright, so let's go ahead, let's read through this one together, let's use our little brains, okay? So let's write down, you gotta pave the trail, equals, you gotta pave the trail. Or track, it doesn't matter, they both start with a T. I think I said track to you guys, so I'll say track. So you gotta pave the track, you gotta pave the track. Okay, so a cylinder of gas is kept at a constant pressure. Okay, stop the train. Out. As the volume decreases from 1.150 liters to 0.860 liters. If the initial temperature was, I'm changing it to Kelvin, 21.8. I'm not even going to try to do math in my head today. I am too sleepy. So 294.8 degrees Kelvin. What's the final temperature? And when you get your final temperature, your answer is going to be in Kelvin because that other temperature is in Kelvin, okay? So let's go ahead and fill in what we know. So I have V1 over T1 is equal to V2 over T2. And I'm just going to fill in the first volume. Look, here's my first volume right here. 1.150 liters. My first temperature is right here. So it was 294.8 degrees Kelvin. And then my second volume is 0.860 liters. Now before I even do this math, you guys, when I'm dividing, it's a direct relationship. So should this temperature be smaller or larger than 294? Should be smaller because as this one goes down, that one has to go down. So that's a good way for you to check your work when you're finished, or at least guess. And so I can see this went down by, you know, maybe like 30%. So this number will go down by about 30%. So the answer should be around 200, maybe a little bit more. But I mean, you can kind of guess. You know, you need to use your brain a little bit. So anyway, that's T2. So now go ahead and you're going to cross multiply and divide. Your way to success here. Knock it out. And that's point. There you go. It looks like I'm limited to 3 sig figs. going to put a decimal after the 0. And that's degrees Kelvin. How does that make you feel? You just want to do some simple math today? Doesn't that sound nice? Gases are really fun. Even in AP, like that's the easiest thing, even though it gets kind of crazy. So let's just check our work, whatever. And they converted it back to Celsius. You just, like if y'all were in AP, we would leave it in Kelvin because like you just don't do gases with Celsius. It's like not right. Unless they tell you to, which, okay, fine. Just, but it's not a big deal. Okay, so what we're going to do is you guys are going to do 1 through 7 for me. And then 8 is a little extra credit, and I'm not going to help you with it. And 5 extra points. And I'll grade this tomorrow real quick before we do the lab. So anyway, go ahead and get started on that. And I'll put the answer key up here in a minute, let you get like a little head start. Should be okay. I need you all to write down the formula, to fill in the values that you know. You don't have to show me the crazy division multiplication part, 'cause that's real clunky for this. But the rest I do want to see, please. And make sure you have units. Sig figs. Thanks.